I understand that.
What's up, sir?
Never mind.
Okay. Let me see. Does it look something like that? Okay. Guys, what's the first step on doing this derivative?
7x minus 8x second to the 1/5.
Is that a natural law, right?
Not
What?
that problem, no. Oh, you mean from the quiz we just took?
Yeah.
I was talking about the quiz I just gave out.
Oh,
Yeah.
never mind.
This one I had questions about already. That one's not too bad, right? So any questions from the quiz I just handed back from last time? Yes? Oh, okay. So everybody had something that looked like you all agree that everybody's 2a looked like this? Did it have exactly these functions? No, but it looked like this, yeah? Okay. So don't get too excited. I couldn't do the prompt for it. How do I take this guy's derivative? What's the derivative of tangent? Is the inside more than just x? Yes, so then what do I have to multiply by? Yeah, either dy dx or y prime. Yeah. What about this guy?
Either 4y.
Yeah, either form y, that's awesome. Times. Okay. And then minus 2, kick ass. So we get 3 secant squared y dy dx. E to the 4y. What's the root of 4 or y?
4 dy dx.
4 dy dx. Right? And then what's the idea for the next step? Get everything with dy dx in it on one side. So this term has it, and this term has it, so I'm going to move that over, subtract it over. Right? Is that right? Okay. And then I can take a dy dx out. Take a dy dx out, divide by all the stuff you don't want, and then you know what dy dx is. Yes? Is that all right? So I'm not sure. Was there a more specific question? Yes.
Adjust this. So now I'm going to
No, it's not done. I mean, at some point I have to keep going. Take a dy dx out. And then I can divide by this stuff, right? So I have dy dx equals -2 over that stuff. Is that all right? And then the second part was, if I tell you that it goes to the point, I don't even know, I'm just going to make one up, pi 3. What does that mean? What do I do? How do I figure out what dy dx is at this point? What am I going to plug in exactly? I just see y's, yeah? So what am I going to plug in for y? 3, yeah. Is there a place for us? No, is there a place for, is there an x in this anywhere?
No.
So if I did see an x, what would I put in place of it?
Pi.
If I do see a y, what do I put in place of it? 3. I gave you a function where the derivative was just dependent on y. Yeah.
You just brought down the 4y, is that what's going on by the e to the 4y? The bottom piece?
Yeah, this is trying to be a 4, I think.
There's a lot.
We put the 4 in front so it looks better. Yeah. On the y, this is here. Okay, that's better. Yeah. Yeah, because I took a dy dx out. I don't know why I had all this extra crap. So then it's just 4 e to the 4y. Should be a 4 here. Yeah.
Okay.
I almost didn't do that step, so I did that step very quickly. Yes?
How about 1D?
Okay, okay.
Like I get the part and it's not a product.
That's not too bad. Triple the cotangent of square root of. There. So, again, what's the first thing you should do before you do anything? How do you rewrite this inside better? Okay, good. Now, again, this is a perfect example where you understandably freak out. But you have to calm yourself down because the only thing you care about when you're about to take a derivative, can somebody tell me what's the only thing you care about for the first step of the derivative? The outside. Right? What's the outside function? Now, if you don't remember the derivative of cotangent, you'll freak out because you're going to get this wrong, but what is the derivative of cotangent?
Negative.
So close. It's a co. Negative.
Cosecant.
No. The secants are the weird secant tangent or negative cosecant cotangent. Derivative tangent secant squared, so derivative cotangent is negative cosecant squared. Yeah. Okay. So derivative of the outside function is that. And then of course what gets a term? Be very specific. What gets a term? 5 minus 7x cubed. What's inside of cotangent? 5 minus 7x cubed. The 1/2. I love it. So one mistake some people did was they just did derivative of this. But what's inside of cotangent? This whole thing. So one thing you can notice from the beginning is there's a function inside of a function inside of a function. So if you want to, you can realize I'm going to have 3 chain rule kind of pieces. Because there's a function in a function in a function, yes? Okay. So here's one, here's a second one, and then this one's going to have a third one, yeah? Maybe you guys see that. So the very first step on this, derivative cotangent, we have it memorized. It's negative cosecant squared of stuff. And then the stuff gets a term. So writing that down is not difficult. Now you focus on this guy's derivative. Is this guy's derivative difficult?
No.
No. Anything to the 1/2 power derivative is really straightforward, yeah? Okay. So, again, when I get a problem like this, it really, at first, does not matter what this is. The only thing that matters at first is the outside is cotangent. That's all that matters at first. When does what is inside matter? The next thing, I got to take the derivative of the, now that matters. Now I care about what that is. How do I take the derivative of this?
1 out front. 5x. No. 5 minus 7 cubed. And negative 1/2.
And this one you can just do, right?
Yeah, that's 5.
What's the derivative of the inside?
Negative
21.
21.
Negative 21x squared. Yeah. So I know I'm done with chain rule because here, for this piece, what's the inside function? X. So I know I'm done. And now I can bring that out front, for example. You guys with me? Do you see how there's a negative here? And a negative there, so it'll become positive. 21x squared, I can put that out front. Over 2, is that cool? So I can put all my single dude together. The numbers and the x squares, and then that can be in front of cosecant squared. And then I got my 5 minus 7x cubed. I got 1/2. Blah, blah. You could even, now some of you guys like to do this, I love it. You could bring that dude down underneath here, right? Because it's a negative power, so it wants to flip. Kick ass. Why can I not multiply this and this? Why can I not multiply those?
Because it's a negative.
Because this one is where? Where's this one? It's inside of the cosecant, yeah? So of course these can't multiply together, because one's inside the cosecant and one isn't. Now listen, you look at everything we just did. That looks, well, to me I think it looks great. But I understand to you this might look disgusting. But every step, you know the derivative of cotangent. And then whatever the hell this is, you just write it. You don't have to think about it. Now you got to think about it, but that's its own piece. You worry about that by itself next. So everybody got what they want from that? More than you wanted? Okay. Anything from homework stuff? Where should you be in the homework? You should be in section 3.9 for sure. You should be trying some of those related rate problems, bringing questions back. Okay. There's one little thing I didn't talk about yet, and I will talk about it.
Are we gonna have word problems in the test?
On the test? Yes. Huh?
Can we add a comment?
At most 2. Like the related rates problems, they're obviously going to be in the next test because we did that section. So.
Is it gonna be a thought similar to what we worked on, or like, I mean?
Yes.
Like, okay.
Yes. So how does a related rates problem work? You set up the function, and then you take its derivative, and then you plug stuff in. Now that's an oversimplification, because set up the function is a huge step. You guys agree? That's where we did weird shit like similar triangles and so forth, right? So, if you try to generalize, all right, let me see. There's not categories that you can do. I know as a student, what you want from me is, whenever I see this, I do exactly this. No, nope. There's an idea. If I can set up the function that relates the variables, I can then take a derivative and relate the rates of change. And then I can plug in what I know. That's the idea. What kind of function could it be? Depends on the situation. So what you do is you try to do enough situations so that when you see something you're like, okay, I kind of have done something sort of like that before, okay, good, right? But there is no real such thing as every time you see this, you do exactly these. No. You guys kind of with me? I know that's not, I'm not going to sugarcoat anything. These problems, you have to set it up according to what the problem says. So drawing a picture is a crazy good idea. If you don't draw a picture for most of those problems, I don't understand you. Drawing a picture and then labeling it, that, dear God, that's going to help out a lot. Because then you'll know, is it the Pythagorean theorem? Is there an angle? Is it trig? Is the sides related somehow? All this kind of stuff. Okay. So if you come back with specific questions, we can do them. And I normally don't on a test. I'm not going to give you something you've absolutely never seen before. That would be, and if you think I do, come and see me, because I didn't. Okay. So if anybody has a specific question from related rates, we'll do it now. Yeah.
27 on the 251.
It's 27. There. Oh yeah. Okay, good. All right. This is kind of funny. I have a handout specifically about this problem because normally I wait till people have tried to do it, and then I have like at the top of the problem it says tough trough problem. Read through that if you haven't looked at this. How many of you guys have tried this problem? Has anybody tried this problem? I know you have, or else that would freak me out that you're asking about it. You're like, that one. All right. If you ever hit a word that you're not sure about, is everybody aware of the word trough? I don't blame you if you're not. If you don't watch any old westerns or whatever, you might not know what the hell a trough is. Like, does that even have you said? I thought it was true. What is a trough? Anybody?
Water for horses or they drink.
Yeah, You fill it with water. Water. You fill it with water for your horsey. Oh, there it went. Okay. You guys all with me? Can you vision it now? Can you see it? Everybody's seen this trough. This trough is weird. It's in the shape of an ice. So the end of it, if I cut it somewhere, it'd have the shape of a trapezoid. Everybody's favorite shape. Does anyone remember the formula for the area of a trapezoid? What does a trapezoid look like? Can you guys,
Rectangle.
like that sort of thing, right? There's a standard trapezoid, yeah? Let me draw it up here. So the funny thing about a trapezoid is, can anyone tell me what that looks like? Doesn't it look like somebody cut the head of a triangle off? If you take a triangle and you cut its head off, you've just made a trapezoid, yes? What did I do? Okay, sorry. That's fine. Think of Game of Thrones. That one's a yes. So what's funny is the area formula for a trapezoid, and do you guys see, if I draw a diagonal, do you see how I make two triangles in there? You see that? Alright, unless somebody really wants to see it. If I do the area of both triangles and add them together, I actually get this. This is kind of interesting. What's the area formula for a triangle? 1/2 base times height. How many bases are there for a trapezoid? Couldn't I turn this around and it would still sit fine? It has 2 bases, doesn't it? So this is the same as the area of a triangle, except it's just the sum of the bases. Are you guys all with me? So it's the height, goes in for h, and you add up the bases inside. Very similar to the form of a triangle because it's a B-headed triangle, or it's, if you cut it up, it's 2 triangles. I think if you, where is it? I can't remember if they have it in here. Script. I don't think they do. Ah, here we go. If you, one of the first things you should look for when you get a brand new book is what formulas do they give me, right? I don't think they give you trapezoid here, do they? That's a little bit evil, but we'll be okay. Oh wait, what's on the other side? No, okay. Alright. So coming back to this problem. So it's 10 meters long. So the trough itself, so I've got a trapezoidal base, right? And it's probably more like this, so that it's got a wider top. You guys with me? So there's a wider area for horses and stuff to come and get some water. And then it's 10 meters long. Are y'all with me? So it looks like, let's see, I normally don't do too horrible with this. So it looks like this, it's got a trapezoidal base. Huh? Okay, give me just a moment. And then it's repeated for 10 meters. You guys all with me? So if I chopped it anywhere, it would have a shape of a trapezoid, right? Okay, maybe. This kind of shape is called a prism. When you have a repeated shape, for example, a cylinder is a prism, because what's the repeated shape? Circle's repeated, right? The formula is always the same. I'm telling you right now, the formula for the volume of both of these is the same. The volume for both of these is the area of the base times the height. Okay, so let's take a look. It tells me, crap, if you do that. So it's 10 meters long. Where do you go? This one, yeah. Cross section is shaped of that is 30 centimeters wide at the bottom, 80 at the top, has a height of 50 centimeters. Okay, so we can kind of label that all on our picture. Just like the problem we had with the conical tank that was being drained or something, I think it was. And we had to draw a representative place where the water might be. So I'm just going to say water, and you're going to deal with it. I'm going to do the same thing here. This trough is being filled because we got a bunch of horses coming over. I'm like, oh shit, how fast is the water level? Okay, blah, blah, blah. Okay. So I'm filling the trough, and I'm curious, how fast is the water level rising at a certain point? why would the water level, if I'm filling it at a constant rate, why would the water level not rise consistently? Because what's it do as you go towards the top? It widens out. So if I'm dumping the same amount of water over whatever time, of course it's going to slow down as it gets to the top because it takes longer. There's more air, surface area for it to fill. Are you guys at all with me? So this problem kind of makes sense. It depends on what height I'm at to know the rate of change of height, because as I go higher, it's going to go less fast. It's going to go slower. Maybe I'm going to stop for a minute. So it's kind of nice just to take a minute and say, does this problem even make physical sense? That's a great place to kind of start. Does it help you do the calculus? No. Does it help you understand the problem? Yeah. If you can see how it makes physical sense. Okay. So help me label my problem. Those of you who have a book, you can see. It tells me the bottom is 30, is that right?
Yeah.
And the top is 80.
Height of 50.
And it tells me the height.
Does that say centimeters or meters?
Centimeters. It's 10 meters and then 80.
Is it meters?
30
Wait.
centimeters. The length is.
Yeah, good. That's something we're going to have to worry about, right? And then the height was 50, is that right?
50 centimeters.
Yeah. Okay. So what is an immediate issue that I want to take care of right now?
Centimeters to meters.
I would rather go meters to centimeters, so don't get decimals. I know we live in the U.S., but do you guys know how many centimeters in a meter? 100. So 10 meters would be how many centimeters? Every meter has 100 centimeters, yes? And I got 10 of them. So I got 1000, otherwise known as 1,000. So now all my units match. And actually, what's more important is what's the rate of volume change here?
2 meters.
Ah, okay. Okay. So we actually probably do want to go the other way. So let me make sure everybody's with me. The physical dimensions they gave me, most of them are in centimeters, except for that one length. The volume rate of change is in meters, yeah? Cubic meters. So let's go back. Let's change everything to meters. So if I had a choice, I'd rather make meters to centimeters because that involves multiplication. Every meter is 100 centimeters. If I want to change these to meters, what does that involve? Division. If 100 centimeters makes a meter, well, 80 centimeters is not 100. So it's less than a full meter, correct? So actually, I just moved the decimal back twice. So this is 0.8 meters. This would be 0.3 meters, and this will be 0.5 meters.
Why is that again?
Let's see. If every centimeter, if 100 centimeters makes 1 meter, you with me?
Yeah.
Then 80 centimeters does not make a full meter, correct?
Yeah.
Okay, so then I would divide by 100 to see.
Point.
0.11. So really just gotta move the decimal back twice. Okay. Metric system is so much better than our system, but we'll keep it. And it just means move the decimal back. I don't have to do times 12 or whatever. Okay. So let me draw this again because I got too much going on. Doesn't have to be a scale or whatever. So this will be 10 meters. This is 0.8 meters. This is 0.3 meters. And this is 0.5 meters. Now I'm just going to pick a place for the water to be. So water's here. How high is the water? Don't bring in a specific height, because that is the snapshot. So how do these problems work? Is the water height changing over time? Totally. Let me see, what do they tell us? Alright, so they tell me 30 centimeters tall, yeah? That's the snapshot. That's not what it always is, correct? Okay. So the water at some point is H. Does this ever change?
No.
The whole thing is 10 meters long, so thank God something stays the same. And what about the, what's the one other thing I don't know? So, here's the water, yes? Do you see it makes a trapezoid? Doesn't the water make a trapezoid?
Yeah.
Do I know how long the base is, the bottom base?
Yeah.
Yes. Do I know the height of it? I call it h. Yes, I know it. What's the one thing, and do I know the length? Yes. What's the one thing I don't know?
Base
The
two.
top base. So we'll just call it B for right now. Is that cool? So now the whole point. So this is as much I'm going to do for you. Help me out. What's the area of the water face? Right. If you just look at this, What's the area that?
0.3 plus B.
It'll be 1/2 times the height times
0.3 plus B.
B plus
0.3.
0.3. Right, it's 1/2 the height times the sum of the bases. The bottom is 0.3, the top is B. That's the area of the face of the water, yes. So what's the volume of water? What's the one dimension I have to add in?
Length.
Good. So I just multiply that by 10. It's that same shape repeated like 10 times, like across 10 meters. So if I multiply this by 10, is everybody cool with that just becomes this? All right, I've done a lot for you, and I need to learn how to just stop it. This stuff is so cool. So now what is the issue that we need to address?
3 terms.
Good, I have 3 variables. I'm supposed to only have 1 for us because we're a single variable calculus. To be really, really, really honest, you could do this, but you don't have enough information to do it directly. What rate do they give us?
0.2 meters cubed.
Yeah, what is the symbols for this? Good, it's a change in volume over time, that's dV/dt. And let me see, did they give us anything else? No. The only other thing they give me is how high the water is at a certain point. So what variable do you think I want to do? In fact, what's the question asking? How fast is the water level rising? So what's the only variable that this problem is interested in and tells me about? H. It tells me the height of the water at a certain time, and it asks me about how quickly the height's changing, yes? So which variable do I want to get rid of? I want to get rid of B. So somehow you have to come up with a relationship between B and H, just like we did last time. It's going to be a little bit weirder, but that's where I'm going to stop that. That's the beginning of this problem, is to draw yourself a picture. You don't necessarily have to do the 3D. You can just do the trapezoid by itself and just know that it's 10 meters long, right? Okay. If I know B is 2H, I'm going to put a 2H there, I'm going to multiply through, and then I'm going to take derivatives. And then I can throw stuff in, yeah? Once I get the equation set up with a single input variable, I take derivatives and I shove what I know in. Yes?
Can you explain when did you get the volume again?
Oh, sorry. So the idea up here was the volume of any repeated shape, bless you, is the area of the shape times like how many times it's repeated. So can you imagine, what do you guys have? If I say record, that's like holy shit. If I say CD, that's like holy shit. So we have streaming shit, which I can't stack. So can you imagine CDs? You guys have seen CDs, remember those? Some people hang it up in the mirrors because they think it somehow blocks radar, which is hilarious, but if you ever see somebody with a CD hanging from this because they think it's going to block the radar and they can just speed, no kids, no. Okay. If I have a CD and know its area and I stack a bunch of them up, wouldn't I just take the area times how many I've stacked up? That's sort of like what the formula is. It's the area of the base, which is trapezoid, times kind of like how many I've stacked up in a row. So you take the area of the trapezoids, everybody cool with that, the trapezoid of water? Times, how much I've got stacked up, times 10. 1/2 times 10 is 5. So I just multiplied this by 10 to get the volume. Okay. So that gets you started. So now you want to focus on, how can I get a relationship between B and H? Anything else? Yes.
You said to take get rid of the B and then take derivatives, what did you say?
Yeah, I want to get a relationship between H and B. Why do I want to get rid of B? Why do I want to replace B with some function of H? Because what is it they ask me about?
B.
What is it they ask me about? How fast is the water rising? That's the height. At a time when the water is 30 centimeters deep, that is also the height. So do I care about the base? Do I care about this? They didn't tell me anything about it, and they didn't ask me anything about it, so I want to get rid of it. I want to replace it with a function of H. The example we did last time was we had similar triangles. Yes? Okay. Yeah.
Do you have time for 33 on the same?
Let's see here. Alright. So car's traveling north, the drone is flying east. At one instant, the drone passes directly over how fast it's okay. Sorry. Yeah, so did you try to draw this?
Yeah, I tried to.
Alright. So it's traveling north on a straight road at 20 meters per second.
Right.
And the drone is flying east at 6 meters per second at an elevation of 25 meters, so this
Yeah.
gets freaky. So at one point, they are, here's my car. Yeah. Here's my drone. Okay. Let me see, let me make sure I got this. So the car is traveling north, and the drone is flying east. Okay. At one instant, the drone passes directly over the car. So it's 25 meters up. Okay, 5 seconds later. So it's 25 meters up in the air. But this guy, so if this guy's traveling north, and let's say this is north, where's this guy going?
Going to the other side, it's going.
It's going east. So how is it moving? At this instant, that drone is directly over the car, yeah?
Yeah.
The car is moving north. I'm calling this north. Where's the drone going?
Going down?
I would say, we're like,
The real world exists in how many dimensions? 3. I've got 2 dimensions here. Where is east?
Are you coming off the page?
Coming right at us! Ah! Okay. Right? That drone, if I wait a moment, it's going to be up in the air, yes?
Yeah.
That drone is coming off the page, right? Okay, I like it. So you might want to try to draw this in a different way, like from overhead maybe or something. So there's a height up. So if you draw it from the back, maybe, let's see, how do I want to draw this the best? If you draw it from overhead, then here's my car. I'm going to put a C on that for car. And the drone is flown over here, yeah? To the east. And my car is driven to the north. So let's say the drone is flown and the car is gone. So the car has gone north and the drone is flown east. I'm looking overhead, correct? Okay. And I want to know how quickly the distance between these two is changing. Now the trick is, let me see if you guys are cool with this. This is all 3-dimensional, right? So I can't look at this as a single triangle because this drone is up in the air, 25 meters. Do you guys, let me see, let me help you out a little bit. If I want to know how far this diagonal is from that diagonal, you with me? I could figure out, do you all agree that this is a right triangle that I just drew? How do you know that's a right triangle? Because this is definitely perpendicular to anything in the base, yes? Okay. So then if I know the height of this, and do you know the height of the drone?
Yeah.
Yeah, so this might be a good way to represent it. It's just kind of weird to try to capture the 3D stuff, especially if you're not used to trying to draw that.
Yeah.
So this could be the drone, this could be the car. You just got to figure out. So you can think this is where they are. One is right overhead. The car drives north, and the drone flies east. You still have a right triangle. It's just not as simple as a triangle's like on a flat surface. Are you guys kind of with me? So that's a good question because it's a little weird to figure out. You've got this whole other dimension of it's in the air. Like, well, how the shit do I do that? Okay, maybe. So we'll see if that helps. Okay. Yeah, if I call this, I don't need to call this H, do I? Because this is the 25 meters changing. Thank the gods, it's not also going up. Okay. What is changing though? Let me make sure everybody understands this picture, because I want this picture to help. So let's say right here is the beginning, the car and the drone. The drone was right overhead, yes?
Yeah.
The drone flew east and the car went north.
Yeah.
So if I look at what I've drawn from overhead, it sort of looks like this. This is the top of this, is this side of the triangle. Are you guys with me? Okay. So this is where the car was. It's driven north. So what do you want to call this side? Any variable you want. That's right, let's call it X. And then this is flying east. What do you want to call this? Watcher. Okay. I like it. And you know what dx dt is? You know what dy dt is, yes? So I want to make sure you guys understand. This is y. That's the drone flying. This is x. That's the car driving. So what is the question asking me to find then? Let me make this a little bit better. Let me put it down. This is y. There we go. The question is asking me how quickly the distance between the car and the drone is changing, yeah? It wants that full length. You can call this equivalent of z. So here's what's kind of cool about. So guys, do you see how this is a right triangle laying down on the bottom of this cube? You guys see that? Or this rectangular solid, whatever the hell. This is a right triangle laying down. So this is just x squared plus y squared equals that squared.
Right.
What's really cool is if I lift this sucker up, it's just x squared plus y squared plus this squared equals this. You just keep adding more stuff. In fact, if you go into 20 dimensions, it's just x squared plus y squared plus z squared plus a squared plus b squared, whatever the shit dimensions. It's kind of silly. So what I'm saying is, how long is z? Well, z squared is equal to x squared plus y squared plus 25 squared. Tubular. Was that funky? Hell yeah. Is it done? Hell no. Alright, so give that one a try. There are a couple like that in the homework, and if those are the ones you're having the most trouble on, okay, those are free. Alright. Let's keep going. Let's see. Last time we got 4-1 done for the most part. Let's see. A couple little things I want to throw in there. So remind me, how do I find critical numbers?
Circle derivative equal to 0.
Or?
Undefined.
Beautiful. So I want to give you some actual concrete examples of both of these. Critical numbers are where what might happen for a function. Critical numbers are the locations where what might happen.
Max, min.
Max or min. Why am I saying might happen? Because last time we talked about like a cubic, kind of looks like it's going to turn and then it doesn't. So it goes flat right at 0, but then it doesn't turn. So that's not a min or a max. So that's why if you find all the critical numbers, they don't all necessarily mean there's a max or a min there. There's could be. So, for example, so if I have this, you guys, how many locations are there where there's a local max or a min? 3. There's this one, yeah? I'll call this A. There's this one, I'll call that B. And then there's this one.
I thought you were gonna do differentials at C.
I didn't ask anything about the derivative. I said, how many locations of local maxes or mins? Does everybody agree that that locally is the highest point? Does everybody agree that this locally is the lowest point? Does the function get lower than this? Hell yeah, but locally, is that a minimum? Yeah. Do you all agree that is locally a maximum? This is like a very pointy mountain. Yeah? Doesn't have to be like this at the top. It can be like this at the top. Holy shit. I agree with you. And this is why, now let me see if you can make this. You're exactly correct. That doesn't mean it's not a max. That is totally a local maximum. Totally. What's true about the derivative here?
Equals
0. It flattens out. What's true about the derivative here?
0.
0. It flattens out. What's true about the derivative here, Conrad?
Fine.
Does it exist?
Undefined. Does not exist, yeah. That's why a max or a min could occur where the derivative is 0, because that means it flattens out. It could turn then, yeah, and that would be a max, or it could turn, that could be a min. Or where the derivative is undefined, because it might do this, what we call a kink. We all have kinks. Functions have kinks? There it is, okay. So that's why, if I ask you to find the critical numbers, you have to find the derivative. Where is it undefined? Where is it 0? Again, does that mean there will definitely be a max or min there? No. Can anyone tell me anything about the slope before I hit the maximum here?
Positive.
Yeah, it's positive slope. After I leave the maximum,
Negative.
negative slope. And here, what's the slope before I hit the minimum?
Negative.
Negative slope. And after I leave the minimum.
Positive.
So it makes sense. If I go down and then up, the middle must be the location of the minimum. And of course, this is, what's true about the slope here?
Positive.
Positive. What's true about the slope after?
Negative.
Negative, okay. It went up to it and down from it. At point x equals c, it is not differentiable. The derivative is undefined. But it is still a maximum. And we can still capture it. We can still figure it out just by figuring out what points makes the function derivative undefined. So let's try an example. Let's do, yeah. Real quick question just on the side. What's the domain of this function? Does anyone see what the domain of this? What's the only part of this function that could have a problem?
D. C.
C, okay. What's C?
0 and 3.
What's the only part of this function that could have a problem? Next to the 1/2, right? I can plug in anything I want to here. I can subtract 3 from any number, I can cube any number. What's true about this? The domain has to be
Positive.
or 0. So 0 to infinity. Are you with me? So from the beginning, we know this function starts at 0. Can I plug a 0 in? Of course I can. No problem, right? Now, help me out with the derivative. Derivative. Help me out with the derivative.
Product rule.
Kick ass. Go for it.
X over, well, I did low D high, high D low. I think you do it differently.
Yeah, there's no quotient here, so I would never do that.
Well, I say that for the
Okay.
product too.
Gotcha. So the derivative of the first piece would be
3, the X minus 3 times 1.
to the
Oh, to the second
Second
power.
power. Times this. And chain rule would just be a 1, is that cool? Whenever the inside function is linear slope 1, chain rule would just be times 1. I'm not going to worry about it. So right, that's the first step of product rule, right? You're the first dude. Plus, how to take care of this piece, of course. 1/2. Negative 1/2. I love it. What do you think I want to do now?
Factor.
Yeah, I want to factor it, because what do I need to do with it? I need to set it equal to 0, or figure out where it's undefined. Now, can anyone tell me, before we even factor this, can you tell me where it's undefined?
0.
0. Right, isn't this now on the bottom? So I can't plug a 0 in now either? Okay, I like it. So officially, this is not differentiable at 0. But 0 could still be the location of our max or min. How the shit do I factor this? How many x minus 3's can I take? I can't take out any numbers, correct?
0.
There's a 3 and a 1/2 here. So I can take out 2 x minus 3's. Does anyone remember how to do the x's now? Why did you say 2 of these? Because I take out the smaller power so that nobody freaks out. Okay, I do that always. So how many x's can I take out?
Negative 1/2.
Negative 1/2, big x. Now to be really honest, well, let's see if I can. I'm going to take a 1/2 out. So that it's sitting out front doesn't bother me anymore. When I take something out, what operation am I applying? Division. So when I divide by 1/2, it's the same thing as multiplying by 2. So if you take out a fraction, you just multiply by the bottom. This is an equal sign. So 2 times 3 is? Holy shit, I had 2 x minus 3's, I took them. What is x to the 1/2 divided by x to the negative 1/2? X. Do I subtract the powers? 1/2 minus negative 1/2 is 1/2 plus 1/2 is a whole. Plus. How many x minus 3's left?
1.
1. And I took out a 1/2, and I took out an x to the negative 1/2. Look at that. That's so pretty. Basically, what we're doing is we're putting all the weird shit outside, and then the inside now is nice, yes? What do we get on the inside? So x minus 3, yeah. Yeah, what's up?
Where did you get the 6x from? I wasn't paying attention for it.
Oh, okay. So, I took out a 1/2, right? Dividing by 1/2 is multiplied by 2. 2 times 3 is 6. With me so far? Whenever I take something out, I'm dividing it. What's 3 divided by 1/2? 3 times.
Oh, okay. So you did the reciprocal?
3 divided by 1/2 is 3 times 2. Yeah, so that's where the 6 came from. I took out both x minus 3's. And I took out x to the negative 1/2. Again, I divided it out, right? So what do I do with powers when I divide, like bases? Subtract. What's 1/2 minus negative 1/2? That's 1/2 plus 1/2. That's a whole x. Okay. So in general, if I take out a fraction, I can multiply. I'm dividing by the fraction, meaning I'm multiplying by its reciprocal. That's how you can do the inside real quick. 2 times 1/2 is? 2 times 1/2 is? 1. That's where there's a 1 coefficient there. Yeah? When I take out a negative power, I'm dividing by that. Well, it's anything divided by x to the negative 1/2. It's that thing times x to the 1/2. Negative power comes up. So then I can just add a 1/2 to everything. What's 1/2 plus 1/2? 1, a whole 1. What's negative 1/2 plus 1/2? 0, no x's. There's no x's here, yeah? I like it, and just in case you say this, no, there's an x minus 3. There's no x's here. Okay, that part needs to become very straightforward. So how do I find my critical numbers?
Set it equal to 0.
Or So we've already identified one critical number, yes? What was the one critical number we identified? It's related to which piece? From the very beginning, we knew something. Yeah, 0 makes this derivative undefined. So one critical number is x equals 0 because of this piece. So what's the two things? Whenever I ask you, find the critical numbers for this function. You take a derivative and where is it undefined? Where is it 0? So what do I get if I set this equal to 0 now? What do I get? What makes this 0? 3. What makes it 0? You guys see that? Add 3 divided by 7. If you set that equal to 0 and solve for x, you'll get this. So what might happen at these three inputs? What might the output? What might be happening at the output? It could be a max, or it could be a min, or it could be a false thing. It could be like, no. Yeah. Yes.
Would it not be square root of 3? Would it not be square root of 3 instead of 3?
Square root of.
It's x minus 3 squared.
No. What makes the 0?
Oh.
Yeah. I'm setting it to 0, so since it's factored, it's just looking at each piece. What makes that 0? What makes that 0? What makes that 0? So is 0 a critical number because it makes it 0? Sort of. What's more important is 0 makes this undefined. Okay. Does anyone remember, once we get the critical numbers, we did something visual?
The what?
Yeah, we made the sign diagram. Everything starts at 0, you guys with me? That's why it's a really good idea to know what the domain is from the beginning. So now I can ignore everything below 0 because it's not even allowed to be used in the first place. What's true about the function derivative at 0? What did we figure out? At 0, what's true about the derivative? Undefined. I'm going to put a u up there. Then I have 3/7, then I have 3. This does not have to be the scale. It's just a quick little visual. It has to be in freaking order though, yeah? So be careful. What goes over these two? What's true about the derivative at those 2 points? 0. Yes. So the whole idea is, do you agree with me that the function we're working with is continuous on its domain? Because it's made up of a polynomial times a radical. You guys with me? We know those are continuous on their domains. So the only place, and the derivative is continuous on its domain. The only place where the sign could change is where it goes through 0. That's what this is all built on. Because this feels like cheating. I only have to plug in one number in those regions. Does everybody see I just made 3 regions? Let's give you a number. Here's 1, here's the 2nd, here's the 3rd. Why is that not a region? Because my function can't even go there. So for example, if I plug a 5 in, is the derivative negative or positive? Well, that's positive always. That's positive for 5, yeah? That's positive, yeah? And that is positive. So the whole thing comes out being positive. I don't care what the number is. Can you plug in your calculator? Sure. Should you need to? No, because all you care is what's the sign. Give me any number between 3/7 and 3.
1.
Holy shit. So if I plug a 1 in, what's the sign of this? It's squared, so of course that's positive. 1 square root of 1 is positive, right? That's positive. Kick ass. So in this whole region is positive. You with me? And then, can somebody give me a number? This is where you're going to be really excited. Give me a number between 0 and 3/7.
1/4
How do you know 1/4 is in there?
is between 0 and 3/7.
How do you know that?
3/7 is pretty close to 1/2.
3/7 is almost 1/2, sure. And 1/4 is a little farther away. But do you see I have to be careful? Do you understand I have to be careful? 1/4 is not that hard to see it is, but you can't always do that. What I would do is just go 1/7, right? But yeah, you gotta be careful. I need you all to understand. Can you very easily see that 1/4 is less than 3/7? No, that's not immediately obvious. It's true, but it's not obvious. You guys agree? So it really sucks when one side is some funky ass number. Oh well. You can, in your calculator, just cut it in half, right? Or I'll just pick 1/7. So, this is always positive, yes? Alright, let me stop right now. Does everybody understand what I'm doing right now? I'm taking a number between these two, because I want to know, is it going up or is it going down? So I'm going to plug a number between these two into the derivative. If the derivative comes out positive, it's going up. If it comes out negative, it's going down. When I plug a 1/7 in, that's always positive. That's always positive. What's the square root of 1/7? I don't know, but is it positive? Yeah.
Whatever.
What's 1/7 times 7? Minus 3 is negative. So positive times positive times positive times negative. Yes.
Is that a Z or an X? Right above the number?
Here,
Yeah.
that's a Z for 0. Yeah. Yeah, just put a line in there just so it doesn't look like a 2. Okay, so this is called a sign diagram. Does somebody remind me? Oh, good Lord. It's already freaking almost 12. What do these mean? What is that? These being negative, what does that mean? Yeah, the function's going down there, yes? How does the function look right at 3/7? What about at 0? How does it look? Is it going up, going down? That's flat, okay. How does it look how does it look in here? Up. How does it look at 3? Flat. How does it look after 3? Up. I like that. Is there a min or a max at 3?
No.
Look at it. If it was a min, it should look like this, yes? Is that a min or a max? Or is that just the place it rested for a second? It just rested, yeah. It was like, I'm going to turn, no, I'm not. And like, all right, screw you. So from the beginning, we knew that. Where did 3 come from? Did it come from this piece? Because it kind of like comes from the right? Isn't that a cubic? What's a cubic look like? That. Is this a tricky, I'm going to turn, no, I'm not. So that's not surprising that it wasn't a max or a min. It's just a little cubic. Do you have to know that ahead of time? Hell no, I can see that right now. Is there a max or a min at 3/7? What is it?
Min.
Min. 3/7, and then whatever the shit you plug it in the function. You can plug it in the calculator, of course. I'm not going to make you use square root of 3/7 by hand. You with me? You would just plug it in the calculator. I have no idea what that is, and I'm okay with that. You with me? So you just plug it in the calculator, yes? What would I get if I plug 3/7 into this? Of course I get 0. I already knew the slope is 0. I want to know where the point is. So I'm going to plug it into the function, yeah? Okay. What's going on at 0, I can't tell because I don't know what's before it, yeah? Okay. This is all 4-1 would ask of you is where's the mins and maxes. Okay. So let's do this. Let's take a break. It is 10 till. So come back at 5 after. If you have any questions, come up and see me. Otherwise, I'll see you in a bit. Turn this. So they come from setting the derivative equal to 0 undefined. They could represent maxes or mins. Okay, I like it. So, for example, this picture I've drawn, try to recreate that real quick. How many local maxes are there?
2.
2. How many local minimums are there? 1. Is there an absolute max?
Yes.
Yes.
Yes. Does that just make inherent sense? I don't even have to explain that, right? Is there an absolute maximum?
Basically,
Yeah.
the
The highest output the function achieves,
Yeah.
right? Oh, sure. Oh, wait, where did I put them? There. Is everybody with me so far? Okay. And each of these are a very basic one. What do I mean by that? Each of these has a derivative of 0. Like, so we're going to move past that. And now I'm going to ask you next level kind of question. Let me do this layer at a time. From a derivative standpoint, why is this a maximum? Not from a visual standpoint, not from any of that. Why is that a maximum just looking at derivatives? What's the derivative back here? What's true about it? Positive. What's true about it over here? So if I just told you the slope is positive to a point and then it's negative from that point, that's all you need to know, that there's a maximum there. Yeah? It went up to it and then down from it. Or from your perspective, up to it and then down from it. But maybe I had it right. Okay. So everybody with me? What's true about the, now here's where we get tricky. Have you guys ever heard in the news that the rate of increase of like inflation is decreasing? Or the rate of change of the unemployment rate is decreasing? Maybe. Okay. How quickly the unemployment rate is going up is decreasing. Are you guys all with me? So during the pandemic, that kind of happened. So the unemployment rate during the pandemic is just really stupid. When you look at any employment graphs, the pandemic just makes the scale stupid because it's like, so unemployment rate could be increasing. The slope is positive. Are you with me? But what's happening to the slope? So the slope is doing what? Getting less positive, therefore the slope is decreasing. Are you with me? All right, let me see. If a function output, if the function outputs are going up, that function is increasing, correct? The slope would be positive. Now we're talking about the next level. Couldn't the slope itself be changing? So if I'm in a car, so I'm in a car and I'm at a certain position. A little bit later, I'm at another position. What's the rate of change? What do we call that for? For a vehicle, for going in a car, the rate of change. The derivative, we call it the what? Speed. That's how fast I'm going, correct? That is how quickly my position is changing. If I slam on my accelerator, and the name gives it away, sort of, it's the acceleration, yes? Isn't my speed increasing? So isn't the rate of change of my position, that itself would be increasing? Are you guys with me? Okay. So not only can a function change over time, do you agree with me that the slope of this function is changing over time? If I wait, so right now the slope is really big, yes? If I go a little further, is it as big as it used to be?
No.
Is it still going up?
Yeah.
But is it going up as steeply?
No.
But wait a little bit more, is it still going up? Is it going up as steeply? No. So can anyone tell me the rate of change of the slope, is it positive or negative as I move around here? Is the rate of change of the slope is it increasing or is it decreasing? It's decreasing. Isn't the rate of which it's going up, isn't that decreasing over time? So, the function itself is going up, so therefore the first derivative is positive, yes, along here. But that rate at which it's increasing is itself decreasing. It's not going up as quickly. And then of course once you get to here, it's gotten to what? Freaking zero, right? So, let's say that
Part if you slam on your gas, like how would you describe that?
yeah, if I slam on my gas, if I'm moving along at a constant velocity, you with me?
Right.
And then I just gun the acceleration, right?
Yeah.
Then my velocity is going to increase. Yeah, so on a curve, it could maybe look like that. Like I'm traveling along and then I hit this, wow, my velocity goes crazy.
So what you're talking about is if it's at a normal pace. That's
Yeah, so let me ask you this. If this was the position of a car, I'm going forward. How do I know that? Because the slope is positive, yes? But what am I doing? Maybe I'm approaching a what? Because what do? I stop. Now the weird thing is, then what do? I start going backwards. So maybe I start to, bye everybody! Oh, forgot my freaking backpack. Right? So I'm like, bye you suckers! And I'm like, oh shit, and I slow down and then I turn around, yes? That's exactly what's going on around here. So if this is home, I'm like, bye everybody! And I'm like, oh shit! So then I slow down, I stop, and then I back up. You guys kind of with me? Okay, does that help you? Is that better?
Yeah,
Okay.
we.
So, real quick. If this is A, can anyone tell me anything about f prime of A? Not exactly what it is, so tell me anything you know about the derivative of A. It's positive. The rate of change of the derivative. How would you represent that with symbols? I'm going to do it 2 different ways. What does this mean? The rate of change of the function, yes? Now I want the rate of change of the derivative. That would just be double prime. So it's positive at A. Is that rate increasing or decreasing? Yes. I'm still going further away from home, correct? But am I going further away from home faster or slower? Slower. So then the second derivative must be negative. I'm slowing down. So if I'm going constant velocity, let's see, how do I say this? If I am speeding up, then I must be accelerating in the direction I'm going. If I'm accelerating, that means that I'm going faster in that direction. Yes? What do we call it when we slow down? What's kind of like the technical name for slowing down? Decelerate. I'm accelerating backwards. It's kind of neat. Okay. I'm not going to suddenly start teaching physics, don't worry.
Will you ever continue going? Is that kind of like an exponential thing?
Sure.
Okay.
Sort of. Of course, there's a top speed for a car, for example. Top speed for everything, really. So you're not going to have this. You're going to have, as you approach your ceiling. Yeah. Okay. All right, let me stop for a minute. So are you with me? If the rate of change of slope is positive, that must mean it's going up faster, and that's exactly the opposite of what this is doing. What's really, really cool, and by the way, let's see if you guys are cool with this. Now I'm going in which direction? Down. So what's F, so let me call this B. What's F prime of B?
Negative.
Yeah, it's negative. See if you guys are cool with this. You ready? What's F double prime of B?
Positive.
No. If it were positive, I should be slowing down. What am I doing as I go down here? Is my slope getting bigger?
Oh, yes.
I am speeding up, aren't I?
Positive once you.
So I go, and then I slow down. Oh shit! And then I stop at the top, and then I start to back up. I'm going to accelerate backwards, right? Hopefully, I'm doing this, where I got my little rear view camera. Get out of the way. Okay. Am I not accelerating backwards then? Going a little faster to get back home? Backwards? Yes. Don't do this, kids. Better. So f prime of b is less than 0, and f double prime of b is also less than 0. At some point, do I start to... Oh, shit. Now, with my analogy, this gets a little silly, but do you see how I shot past the house? Let's just go with it. Did we agree that the house is kind of like here? Right? So if I go, didn't I shoot past the house? So if I shoot past the house, what am I going to start to do? Like, oh shit, okay. I'm going to start to slow down, and then I'm going to go forward again. So does everybody agree that at some point, the slope stops getting bigger, negative, and starts getting smaller, negative? So at some point in here, and we talked about this point before, it reaches its biggest negative slope. And then it starts to get less negative. So at some point in here, so like let's say this is C. At C, What's true about the slope of the function? It's still negative, but the second derivative is positive, because now it's going less negative. It's starting to get smaller. The slope is getting smaller. Does everybody agree that the slope is definitely getting smaller? So they're acting against each other. Okay. What's really cool visually, everywhere our slope was negative, can anyone tell me, is there a shape that it is when the slope is negative? I'm sorry, the second derivative is negative. Does everybody agree the second derivative is negative all the way around here? That's what we discovered. Second derivative is negative there, second derivative is negative there. All the way through here, yes? Versus the second derivative here is positive. Throughout this whole region, is the second derivative getting more and more positive? Yes. What's really cool is visually, when the second derivative is negative, it's cupped down. It's sad. When the second derivative is positive,
It's happy.
yeah, it's cupped up. Yeah, it's psychotic levels of happy, it looks like, yes. So it's what we call, unofficially we call this cup down, cup up. It's kind of nifty. So if I have a cup down situation, that means that I'm starting to accelerate backwards. So that's, the second derivative will be negative. If I have a cup up, that means I'm starting to accelerate forwards. That means the second derivative is positive. It's kind of a beautiful, thank the gods that the visual of it is so in your face. Yeah.
Remember when the second derivative equals 0, that's when it
Yeah, that's where weird things happen. That's, so, just, really, y'all agree with me that the slope here is 0. It starts to build bigger and bigger negative, doesn't it? Slope here is 0, yes? It was growing smaller as it approached there. Does everybody agree that somewhere in there, it's the most negative? That point right there, I'm going to call that point I, because I'm a weirdo. Does anyone know what that point's called? I know some of you guys know. I gave it I for a reason. Yeah, inflection. It's called the inflection point. Has anyone ever heard that word before? Inflection? Not even mathematically. Sometimes you hear that in the news. Believe it or not, you're all like, the what? I don't blame you. News sucks. Okay. Yes?
What did you say that inflection point describes, where it's,
The place where it stops getting more, for example, this inflection point, it's not getting more negative, it's starting to get less negative.
so like the point where it kind of shifts?
Yes, and visually, what's really cool is, that shape right there, is that cup up or cup down? Cup down. That would not hold water, yes? That shape right there, is that cup up or cup down? Cup up. So that inflection point is where it goes from being cup down to cup up. To make this more technical, this is called concavity. This is concave down. So that's cup down. This is concave up. Cup up. So this is kind of cool. Critical numbers are where it could stop going up and start going down, or stop going down and start going up. Are you guys with me? Critical numbers for the first derivative are where that transition happens. It stops going down and it starts going up. It could do that, or it stops going up and it starts going down. That could be what happens at the critical numbers for the first derivative. Are you with me? Here, inflection points are where it stops being cup down and becomes cup up, or stops being cup up and becomes cup down. It's where the concavity changes. So first derivative critical numbers are where the increasing, decreasing might change. Critical numbers for the second derivative are where the concavity might change. So if I ask you guys, can you make a picture of a polynomial? Just make a general polynomial. I'm curious now. Can you guys draw just a general polynomial? Can you guys do that? Huh?
What degree?
I don't care.
X4.
So, but maybe more than a parabola? Yeah?
X4 would be like a W.
Totally, that's one example, sure, but go ahead. Just draw your favorite little polynomial. If you don't have one, figure out what your favorite is. Maybe more than a polynomial, but
Or sine graph.
yeah, sine graph is not really a polynomial, but yeah. So then, I would assume that most of you guys would do something like that, maybe. But you can keep going if you wanted to, right? Do you guys agree? Can you guys see that that's naturally broken up into cup up and cup down?
Yeah.
Okay. Polynomials are not the only functions that have this, but they're the most obvious, right? And they're the ones you work with a decent amount in pre-calculus. You talk about number of turning points, the fundamental theorem of algebra, right? Can anybody tell me what the smallest degree might be of the function I just drew? You guys remember how to do that? What's the smallest degree this could be? X squared, how many turning points does it have? And what was the degree of it? 2. This is how many turning points? 4 turning points. So what's the smallest degree to be? 5th. One more than the turning points. You with me? Every freaking x squared has 1 turning point, correct? You with me? X cubed could look like this. So it has at most 2 turning points. So how many turning points could a polynomial have? At most 1 less than the degree. Does that sound at all familiar? And if and how many intercepts are there for this guy?
4?
Yeah, there's sort of 5. I want this guy to hit. Yeah. All right. Okay. So you all agree this is definitely, what would this be? Cup up. And then somewhere in here it transitions to cup down, yes? And then somewhere in here maybe it transitions to cup up again. You guys all with me? So you can sort of naturally discover the inflection points. If I take the second derivative, help me out, what would the second derivative here be? What's true about the second derivative in this whole region here? Is cup up, yes? Is it happy or sad? Scary happy. So this is positive, yes? What's true about the second derivative here? Negative. So what do you think happens if I truly have an inflection point? What do you think happens at that inflection point? That's where the f double prime is? 0. That's the transition point. It transitions from cup up to cup down or vice versa. So it must be 0 right there, just like critical numbers for the first derivative. If it's going up and then going down, it must be 0 in the middle. If it's cup up and the cup down, it must be 0 in the middle because it's positive to negative. So it must be 0 in the middle. You guys, this kind of kicks ass. So how do I find critical numbers to see where local maxes and mins are? Set the first derivative equal to 0 or see where it's undefined. How do I find critical numbers for where inflection points might happen? Set the second derivative equal to 0 or see where it's undefined. That's kind of beautiful. It's the same process, just with different derivatives. First derivative tells you if it's going up or going down. Second derivative tells you is it cup up or cup down. You're like, yeah, yay, Jeff. Okay. So, by the way, let me just put this out there. I'm skipping 4.2 for the moment. We're going to come back and do 4.2, but I want to focus on 4.3 and 4.5 because they're both basically the same, to be honest. And they both have the same idea. So let me give you this. So now you know why it says 4.3, 4.5 at the top. I'm going to do this, the front together, and then I'm going to make you do the back yourself, which might be a little evil, but we'll see. So let's take a look. Here, let's look at this, let me think. Yeah, let's do the one in the back together, because that's a little bit worse. And then I'll let you do the one in the front. Does everybody agree with me that function on number 2 is a little worse? One thing I will always do for you on a quiz or a test is I will tell you what the first derivative and what the second derivative should be, yes? So if you have trouble getting the derivative, you can still do the rest of the problem, you understand? If you couldn't get the derivative, you're screwed, you lose a lot of points because you can't do it. So I want to tell you what it should be. If you can't get there, go, oh shit, and then just finish out the problem. You can do the rest of the problem now, right? So, let's do this in the interest of time. Let's see, maybe I still want to do it. How would I rewrite this before I find... Actually, let's do this first. Anybody can see the domain of this? Yeah, the smallest x could be a 0, yes, just like the one we just did. So the domain is 0 to infinity. How would I rewrite this?
X to the 3 over 2
Good, x to the power over root.
minus 3x, so 1/2.
Good. Radical cuts things in half. There you go. Square root. Somebody with me? Definitely rewrite. That's why radical notation sucks, just generally. Do the first step for finding the derivative. Because does that look like what you would expect it to be? No. Maybe. Okay, I like that. But this, I don't see that, do I? So try it. Do the first step on the derivative. So this is what it should end up looking like. I want to see what we get. Is that right? Of course, this would be the 1/2 again.
Why is it, wait.
We're going to find out. Again,
Okay, I'm gonna.
yeah, don't
what
worry.
do you think?
The end result of a derivative, it does not look like that until you're basically done with it. So never give up when you're like, I'm not getting anywhere near that. Well, yeah, not yet. You don't know. Keep going. How do you take the derivative of 3x to the 1/2? It'll be,
3 over 2.
the 1/2 comes down, and then it's x to the,
Negative 1/2.
alright. So that still doesn't look the same, does it? But we all know what we're about to do. We're about to set this thing equal to 0. And also, where's it undefined? But to set it equal to 0, what should it be? It should be factored. So I take out a 3/2. And how many x's can I take out?
Negative 1/2.
Good, you always take out the smaller power. Why? Because you always do. Right? We talked about that. X cubed plus x to the 5th. You take out x cubed, the smaller power. Yeah? You always take out the smaller power. So I took out a 3/2, that's gone. I had x to the 1/2. I divided by x to the negative 1/2. So how many x's do I have?
X.
1x. When you divide by a negative power thing, it's the same thing as multiplying by that thing. So I just add 1/2 to both the powers. Yes? Divided by x to the negative 1/2 is the same as multiplied by x to the 1/2. So I just add the powers when I do that. 1/2 plus 1/2 makes a whole. And the 3/2 came out. 1/2 plus negative 1/2 is 0. So I have no x's in the next term. Okay, I like it. Hey, Mikey. So if you get to this point and you're like, I forgot to factor this shit, you'll get some credit for that, and you can keep going because I will tell you what it's supposed to be. Yes? Okay. What are my critical numbers?
1 and 0.
Yeah, why is 0 an answer?
Because it's always there.
It makes, no, it's not always 0. Come on now.
Because when you pull it out and it's in front, that's what makes it.
Because of the fact.
What does 0 do to the derivative? Makes it undefined. So it's 0 because it's undefined there. And why is 1 an answer? Because the derivative is, when I plug a 1, I get 0. Yes?
What would be the case when one of the answers is not 0?
Then you don't write 0. I'm not sure. Okay.
Because in this example, x could equal 0, but is there like ever a problem where it won't equal
course, yeah, totally. We've actually seen that kind of problem before. Real quick, side note, because the other example on the back has 0, but if I had this, let me see if we can do this real quick. If I had that, I'm going to take it real quick. And I'm going to factor it real quick. Let me see. Jeff, you can do better. Okay. So then I get x minus 1, x plus 3 squared, 5x plus 3. Okay. Is 0 an answer for a critical number?
No.
Why? Does it make it undefined? Nope. Does it make it 0? Nope. Okay. So very easy for a critical number to not include 0, right? That's an example right there. Unfortunately, I just made 2 examples that has 0 as a critical number, but it doesn't have to always be. Why is it an answer here? Because it makes it undefined. What if it doesn't make it 0 undefined? Then it's not a critical number. Okay, I like it. Making a sign diagram. It's undefined at 0, and it's 0 at 1. Yes?
Oh, okay, I just realized you put U and Z for undefined, right?
Yeah. What do I do? By the way, square root of x for x is above 0 is always what? Positive or negative? Square root of x for x is above 0. It's positive, yes? Do you guys see that? So isn't the sign going to be determined by what this is? Above 1, this is positive. Below 1, that is? Okay, then all I care about is what's the sign of it. I don't care what the number is. Right? Now, if you want to, you can pick 2. You put 2 in. Square root of 2 is positive. 2 minus 1 is positive. Again, I don't give a shit what the square root of 2 is. I just need to know it's positive. Because that means the function's going up. If I plug in a 1/2, square root of 1/2 is positive, whatever the shit that is. And 1/2 minus 1 is negative. So then I know it's negative in here, right? Yeah.
Is the only reason we're not finding anything less than 0 because of that root? I mean, we know it can't be less than 0.
Yeah, the domain starts at 0, so the function can't even handle numbers below 0.
So
That's
say we
totally
get-
out of my consideration.
Sorry, so say we get another equation where it is an undefined part of it, right? Would we still kind of plug in?
No, be careful. I can have a location that's like for example, this is undefined at 1, yes? But it exists on both sides of 1, yes? Okay. This is a radical, so it just sort of stops here. It can't handle negative inputs. Because thankfully we're not graphing complex derivative functions yet.
Yeah.
You can if you want to.
Oh.
Then we have to get some color pencils. Okay. What does this mean? Can somebody tell me an interval where this is decreasing?
0 to 1.
0 to 1. Can somebody tell me an interval where it's increasing?
Number 2.
More than that. 1 to
Okay.
infinity. Because it's never. Is there another place where the derivative is 0 after this? No, because we found everywhere this sucker is 0, didn't we? So it can never change sign ever again because it doesn't go through 0. If I have a continuous function that's increasing, what's the only way it can start to decrease is if it first goes through 0. So that's why I only have to plug one number in on either side of this because it's going to stay the same sign forever because there's no other zeros. That's the only way it can change sign. Can you draw underneath here? Don't worry about the undefined thing. Don't worry about that. What's it doing in this region here?
Negative.
Going down. Here it's, which means it's flat. And here it's going up forever. Yeah. So it should have kind of a down thing. We don't know exactly what's happening at 0. But we know it should go down from whatever is 0, and then it should turn, and it should come up forever. Yes.
Do we necessarily have to do the down arrow to flatten and up? Do we have to do that in the test?
Do you have to? No. Is it a decent idea to do it? Yeah, because now can you tell me just from what we did, is that a max or a min at 1? So tell me exactly where the minimum happens. 1, what?
What?
Plug it on.
Plug in 1 where?
Original function.
Original function.
-2.
I'm not asking what the slope is now. I want to know where the function is. So you have to plug 1 into the original.
-2.
Yeah, when you plug it in, you get square root of 1 is 1 minus 3 times 1, so 1 minus 3, -2. Is there a local max to this thing?
0?
This is gonna be, yeah, 0. So let's see. How do I know there's a local max at 0? Because it's going down from 0, yeah? And the other side doesn't even exist, so there's sort of like a max here. So what's the location of the maximum? 0,
0.
0. And again, that's a local max, yes? Okay. Just stop for a minute. I always like 0, 0 because it looks like a little face looking at you. Okay. Take a minute. What was the first derivative again? There it is, right? Just work with this, figure out what the second derivative is. You already know what it should be, but it's not going to look like that until the end. So try to do the second derivative. All the second derivative is the derivative of the derivative. Let's be honest. Let me show you a little trick. If you use this, what rule do you have to use? Product rule. Does everybody agree this is also the derivative?
Yeah.
Do you have to use product rule in this form?
No.
So it's up to you. Does everybody agree with me? And I could have gone insane, so you could disagree, because maybe I just went insane. This is the same as this. This is the same as this. You all agree with me? I love you guys so much. X plus 2 plus 3, is that the same as x plus 5?
Yeah.
Yeah, of course, I just simplified. So these are completely the same. All I did was I took this and I factored it. So of course it's the same. Otherwise you don't believe that 12 is the same as 3 times 4. Of course they are, I just factored it, who cares? So what I always did was I went back to this step to do the second derivative, because then I don't have to use product rule. But you can do it either way you want to, right? So I would do this, I would do 1/2 comes down, makes this 3/4. And then negative 1/2 comes down and makes this plus 3/4. X to the negative 3/2, is that cool? I'll do it the other way too, in case you guys were doing it that way. And then if I factor this, what comes out?
3/4 x.
What's the
minus
lower power?
Negative 3/2.
Yeah, negative 3/2 is definitely lower than negative 1/2, yeah? Now let's see if everybody's with me in there. And when I divide by x to the negative 3/2, it's the same thing as multiplying by x to the 3/2. Let me say this again. Yes, sorry, go ahead.
Where did the 3/4 x come from afterwards?
Where the what now?
The 3/4 x? The 1 plus, or the plus 3/4 x?
Because you bring down the
This
negative
here?
1/2.
Wait, what's happening? So right now, all I'm doing is I'm taking this out of both. Yes? That's what I'm taking out. That's all I've written. So now I gotta write what's left. Are you with me? I'm just taking out the GCF. So I can take a 3/4 out of both, yes? And I can take the lower power out of both. So now I'm gonna write what's left in the first two. When I divide by x to the negative 3/2, it's the same thing as multiply by x to the 3/2. Whenever I take out a negative power, I'm going to add that power to everything with a base of x. Does that make sense? If I divide by x to the negative 3/2, it's the same as multiply by x to the positive 3/2. So what is negative 1/2 plus 3/2? Negative 1/2 plus 3/2.
1.
2 halves, which is 1. Plus, I took out a 3/4 and I took out that, so what's left over here? 1. So we got the same answer there.
Well, but wouldn't the x be equal to -1?
Yeah, total, yeah. Critical number, yeah. That's fine.
But that
No.
doesn't fit in the domain.
Beautiful. So do I have to consider it then?
No.
No, beautiful. So it could have a critical number in -1, but that's not even in the domain. I love it. So real quick, if I do this the other way, in case anybody did it, if I start here, the derivative, I have to use product rule, right? So the -1/2 will come down, times this, plus the first dude. What's the derivative of x minus 1?
1.
Then you have to distribute this, right? Or you don't really have to. You can, anyway, it's a little bit worse. You could distribute it and then take it out, or you could take out something from both of these. You guys see what I'm saying? So let's do that. What can come out? This is definitely worse. What can come out of these?
3/4?
Sure, 3/4, okay. And x to the what?
-3.
X to the -3/2. So I'm left with a negative
1.
x minus 1
Oh.
plus, now here's where things get nifty. What's 3/2 divided by 3/4? That's 3/2 times 4/3. 3's cancels, 4 divided by 2 is 2. And of course we already did like -1/2 plus 3/2 is 2/2. Are you guys already on my side here in doing it the other way? Just to show you, we get the same thing. This will be -x plus 2x is x, -1 is plus 1. Is that the same thing we got? Yes. In a worse way? Yes. So, I desperately want you guys to understand. What do I tell you the first thing you do? If I say take the derivative of these, you look at each one, what's the first thing you look for? When I say take the derivative of this, what do you look for first?
Powers.
If I'm able to simplify. Shit, yeah. If it's a quotient and I can factor the top and kill the bottom, it's not a quotient anymore. Sweet, because quotient rule sucks. You guys with me? I kind of agree with you on that. I still haven't shown you what I did. I never used quotient rule when I was a student, but it kind of made things harder on me. But anyway, too bad for me. If I can simplify the function first, shit, yes. So look at our options. These two are the same, yes? You have to, because all we did was factor it. This one requires product rule, this one doesn't. So if I need to find the derivative of this, I'm going to choose that form. Sorry for anybody in the next room. You guys kind of with me? I had a class where the guy next to me was like really adamant, and we were all guessing what his Morse code was. Please help me. All right, hopefully you guys understand. If I have multiple forms of the same function, I pick the one that's easiest to take the derivative if I need to take the derivative. That's the bottom line. Now, what are the critical numbers for the second derivative? Yeah, -1 and 0. Why -1 could be? Because it makes this 0. But, like somebody pointed out, is that in our domain? Nope, so I can ignore it. And why is 0 a critical number?
Because it was one before. It was a critical number.
No. Why is 0 a critical number right now?
Oh.
Because it makes this undefined. I love it. Okay. So if I make a sign diagram, so it's 0, it's undefined. What's neat is are there any other critical numbers in our domain? No. So are there any possible inflection points? Remember, inflection points is where it goes from negative to positive concavity. If that's your only critical point and it's at the beginning, there's no possible inflection points. Whatever number I plug in, is this positive or negative? Yeah, any number I plug in above 0, this sucker's positive. So this is always concave up. How does that relate to our little quick sketch here? Isn't this concave up everywhere, yeah? So this is not surprising. But again, don't be careful. Don't come right after this and say, because there could be more happening, especially if it's undefined place or something. So don't think this is perfect. But here, this verifies, oh yeah, you get pretty close. It's concave up. All right. So here's going to be everybody's favorite step. So here's all the calculus of this, yes? What did we discover? What does the second derivative tell us about again? What's the official word?
Concavity.
Concavity. It tells me where it's concave down, concave up. So this is always concave up. And of course, this tells me the slope. So this should sound a lot like precalculus. And that's because it intercepts. Going back to the function itself. How do I find the intercepts of this? You write this in a better way. We already wrote it in a better way, but just to write it again. In general, if I give you a function, how do you find the intercepts? To find the x-intercept, you set it equal to 0, correct? To find the y-intercept, so let's do the y-intercept first, that's the easy one. If I plug 0 in, I of course get, if I plug 0 in, I get 0 out, and we kind of already knew that. Already knew that was a point it went through, right? Okay. How do I get the x-intercept? Set the function equal to 0, which involves me having to do what? Am I going to do any calculus on this? No, I'm just trying to solve this equation, right? How do I solve any equation that has powers on the x that equals 0?
Algebra.
It's a little broad of a statement. Do math to it! What specific math do I do to it? Factor it, kick ass, right? We always factor shit. If it's higher degrees on the x than 1, I gotta factor it.
Take out an x to the 1/2.
Kick ass, take out the smallest one I can. 3/2 minus 1/2 is 2/2, which is 1. I like it. And of course, 3 is left in there. So what are my two x-intercepts?
0.
The one we already knew.
3 and 0.
Look, now he's judging us, this guy. And x equals 3, right? So 0, 0, and 3, 0 are my two x-intercepts. And of course, 0, 0 is automatically a y-intercept. What else do I ask you to find?
Max and mins.
Max's mins, we found that up here, right? Where'd it go? Our max is 0, 0, our min is 1, negative 2.
Inflection point.
Yeah, do we have any inflection points? No, because it's always concave up. Except for right there where things start, it's a little weird. Increasing, decreasing, we got, okay, so here we go, you ready? So I'm gonna plot everything I know. I know 0, 0 is an intercept. I know, what else? I know 3, 0 is an intercept. I know let's do doesn't look like I need my scale to be anything too crazy. I know the local max is 0, 0. What's the local min again?
1, -2.
1, -2. And then I know that this thing is concave up forever, yes? So how am I going to kind of piece this thing together? Go down and up. Yeah, it's crazy. Now, is that perfect? No. Is that good enough for us? Hell yeah. Yes?
What about the other side?
From the beginning, what did we know? The lowest number I can plug in is 0, right?
Yeah, keep
So the other side doesn't exist.
I keep getting that, so.
We're cool with square root going like that. So of course we're cool with this. It's got a bunch of roots in it. It kind of makes sense. It's got some issues with negative. Yeah. How do you check this?
Drop it on the calculator.
Yeah, let's plug it in the calculator. Okay, now you guys get as far as you can with the problem on the other side. Feel free to huddle up with people near you. I'm not going to make you repeat what we had last time. Went around the room. Oh yeah, that's right. Okay, that works out perfect. Yeah. Good. Yeah. Minus. So write down that. Yeah. And then you know you're going to want to set it equal to 0, so you know you're going to want to factor it. Yeah. Again, don't get discouraged if your f prime doesn't look like mine, because it won't until the end. I'm going to catch up to you guys. Let's see. This derivative is pretty straightforward, right? You're like, give me more of this, Jeff. And factoring it should be pretty easy. Is everybody agreeing with me that is the derivative, yes?
Yes.
What I'm about to do is just simplify it. So if I want to take a second derivative, I could use either form because they're both the same freaking function. So when I go to take a second derivative, you better believe I'm going to use this form of it. Holy shit. How do I factor this?
15x squared. Couldn't say the other stuff.
I took this whole thing out, divided by this is 1. I had
Yeah.
15, took it. I had
1
4
minus x
x's, took
squared.
2. So I'm left with 2 x's. Good. And of course, this is a difference of squares. 1 is 1 times 1. X squared is x times x. Plus minus. Is that the same thing?
Guess so.
No guessing. There's no guessing in calculus. Yes, there is, but not right now. So what are my critical numbers? 0, 1, negative. Take X. You guys all with me? Why would I not want to use this form to do a second derivative? What would that involve? Triple product rule. Yeah? No thank you. I'm going to use this freaking thing because it's the same thing. We're not quite there yet, we're just a ton. So what am I going to put on my sign diagram? And what's my domain? I didn't ask, but I mean, what's the domain of this guy? All numbers, yeah. It's a polynomial. It's cool with everything. So I'm not going to be able to just stop at 0 like we did before. So negative 1, 0, 1. Above each of those, what am I going to put? Each of them make the derivative what?
0.
0. Do you guys remember the idea of multiplicity? All right, let me ask real quick. Have you guys done the sign diagram already?
Yeah.
Anybody? Everybody? Most of you? So watch this. You ready? Multiplicity kicks so much ass. Does anyone remember what that means besides the movie with Michael Keaton?
Is it P over Q?
This is a multiplicity of 2. 0 shows up twice, which means around 0 it looks like a parabola. Meaning more specifically, it does not change signs around 0. So watch this shit. I'm going to put 5 in. Positive, positive, negative. Is everybody with me? So it's negative here. The multiplicity of 1 is 1, so it's going to change signs. Multiplicity of 0 is 2, it's going to stay the same sign. Multiplicity of negative 1 is 1, so it's going to change signs. Thank you, I'm done. Yay, right? Do you have to do what I just did? No. Isn't what I did freaking awesome as shit? Yeah, not because I'm awesome, because it's awesome. Sorry? Yeah, so does everybody agree that if I plug in something bigger than 1, this is negative? Does everybody agree that if I plug in something smaller than 1, this is positive? It will change signs around 1. If I plug in something bigger than 0, this is positive. If I plug in something less than 0, this is positive. It doesn't change signs around 0. So if I know it's negative here, it'll change signs around 1, so it's positive there. It won't change signs around 0, so it's still positive there. It will change signs around -1, so it's negative. Do you have to do what I just did? Do you ever have to use multiplicity? No, you just plug shit in. Did you try to plug a 1/2 in?
Yep.
Alright, positive, 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 right? Try to throw a -1/2 in, positive, 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 yes? If you try to throw in -18 billion or -2, positive, negative, positive, negative. Are you guys all with me? The beautiful thing about the sign diagram is I don't care what the number is, I just care about what the sign is. So you can do it very quickly. I don't care if the answer is -0.478, it just matters that it's negative. So when I plug a -1/2 in, anything squared is positive. 1 minus 1/2 is positive. I'm sorry, 1 minus 1/2 is positive, and 1 minus -1/2 is positive. Sorry, go ahead.
What about E over Q? What's that?
What? Sorry? Oh, we're not, no, dude. Are you talking about like, we're not trying to find the rational zeros, right? We already know the rational zeros.
Oh,
Yeah, I don't have the synthetic division. Is that what you're worried about?
yeah.
No.
That's perfect.
So can you guys tell me what's it look like here? Going down, flat, up, flat, up, flat, down. Okay. So it's gonna look like, sort of, right, it's gonna go, let me see from your perspective, it's gonna go down, flat, up, flat, down. What's the end behavior?
Positive?
The biggest degree is 5th degree, right? So it should be some kind of cubic at the ends. And it's negative, so it's gonna be flipped. And that's exactly what I'm seeing here, right? It goes down and then up at the other side, okay. Second derivative, let me see what time it is, okay. Let's do one more step here, then we'll call it a day. I'm gonna start here when I do the second derivative. So that would get 30x minus 60x cubed. Much nicer than doing a triple product rule. Then if I factor this, I get, what comes out? 30x. 1 minus 2x squared. So how do I find the critical numbers? This is my favorite. You can't just look at it.
0 and
Yeah, good.
plus or minus 100.
No. You have to set this equal to 0. Right? If I add 2x squared, divide by 2, and then what's the last step? So plus or minus, maybe you said it.
The square root of 100.
Square root, there it is. Which is plus or minus square root of 2 over 2. Yes? Square root of 1 is 1, square root of 2 is square root of 2. Rationalize. You should be used to that from trig, yes?
Yeah.
That should look very familiar. So how many critical numbers did we get for the second derivative? Did we collect them all? 0? What's another one? Negative rad 2 over 2? Positive rad 2 over 2. So we got 3 critical numbers. And then the funny thing is, we'll do the rest of this next time, but when I just make a sign diagram, I do exactly the same work here, except if I got a negative somewhere, that means cup down. If I got a positive somewhere, that means cup up. So I just draw little cups. If you guys are with me. So if on the first derivative sign diagram, a negative means it's going down. On the second derivative sign diagram, a negative means it's cup down. Okay. It's up to you guys. Do you want to do this step? Okay, here we go. I just don't want to keep you too long because I didn't give you 2 breaks. What I'm going to put down here? Yeah, negative rad 2 over 2. Jiminy Jeebus. You're telling me that's what that says. Holy shit, Jim. Negative rad 2 over 2. 0,
Right, you have two.
and positive rad 2 over 2. So for my multiplicity people, when I break this apart, it would be two first degree things, so everybody's got a multiplicity of 1, so it changes sign every time. That makes it so stupid quick. If I plug in, what's bigger than rad 2 over 2? Let's say 10. Is 10 bigger than rad 2 divided by 2?
Yeah.
Yes. So when I plug a 10 in, what do I get? Positive times 1 minus twice 10 squared
Negative.
is negative. That's all I care about. Positive times negative is negative. So it's, let me put zeros up here. So it's negative. Everything's multiplicity 1, so it just changes sign, changes sign, changes sign, changes sign. That's the power of multiplicity. If you don't like multiplicity, then get a number between 0 and rad 2 over 2 and plug it in. It's up to you, right? If you really want to do that.
So for the sign diagram, we're always plugging into that function's derivative.
Yes, I'm investigating concavity. Which thing have we done that talks about concavity? Second derivative. So I must plug in my kind of region numbers into the second derivative. So what's true down here? It's cup, up, cup, down,
Up.
up,
And then
down. Let's kind of compare it to what we got. Cup, up. This is still, and then cup down. So we're going to see this better here in a minute. Okay. Anyway, I'm not going to. Yes.
Sorry, when you have a 0 as a critical number, how do you know if it's undefined or not?
Oh, from the function itself. So every derivative, the function, the derivatives were all polynomials. By definition, there's nowhere it's undefined. There's no radicals. There's nothing on the bottom, correct? If I had a function like natural log, man, natural log is not good. If I had a radical, its derivative could have a 0 as undefined, right? Because radical x would become 1 over 2 radical x when you take a derivative. So 0 wouldn't work. You see what I'm saying?
Yes.
If I have a polynomial, I'm never going to have undefined anything. That's why we call them that's why we gave them a name. We're like, these things are so nice. They're so nice. Let's give them a name. And we gave them the name polynomial. It's like naming your kid Bartholomew or something. But still, we gave it a name because we like them. All right. I love you guys. You want to keep going? Okay. Yes. Okay. All right. So is everybody cool with what's happened here?
honestly, I'm confused on inside where it's like plus and negative. Do you know what I'm saying? Inside the rad 2.
So how did I get this negative? I picked 10.
Yeah,
Why did I pick 10?
Because
it's
it's
definitely
a
up
whole
here.
bigger than.
And when I plugged a 10 in to here, I got a negative output.
Correct.
Alright, so if you wanted to, what's between 0 and rad 2 over 2? Rad 2 over 2 is about 0.7.
So
Okay.
So 0.1, you agree 0.1 is in there?
Yeah.
Okay, so if I plug a 0.1 in, 110. 0.1 times this is positive, right?
Yeah.
And then 1 minus twice 100th is also positive.
Yeah.
1 minus a number
Okay.
way smaller than 1 is positive.
Alright, now I got you.
Yeah, so each one, you have to figure out a number that's between those two and see what it is. Why do I only have to pick one number? Because it can only change sign if it goes through 0 or undefined. So I only have to pick one representative number between, and then I know it's negative in the whole region. Now, me, did I do that? No! I was like, oh yeah, there's this whole class called pre-calculus. And in pre-calculus, we learned about freaking multiplicities. So when I factor this shit, I'm going to get 2 first-degree terms. Everything's got a multiplicity of 1, meaning it changes sign around every one of its zeros. It goes through, it doesn't turn, it doesn't bounce. Whatever you guys call it in your pre-calc class. Took pre-calculus, doesn't sound familiar? Slap your teacher, I don't know. They didn't teach you, I don't know. Right? Okay. Do you have to use multiplicity? No. Will it make it quicker? Oh, hell yeah. So, let's take a look here. Finding intercepts. This is all voluntary right now for you guys. If you want to head out, you can. I'll probably do this again next time. How do I find the intercepts? How do I find the x-intercepts? Set this equal to 0. And and then I factor it. Is that alright so far? You guys okay out there? Yeah? So I get one, I'll do this one. Whew. So we also know the y-intercept 2 right now, don't we? That's nice. How do we get to another 2 intercepts, x-intercepts? Set this equal to 0. So I add 3x squared, divide by 3, take a square root, and then I can plug that in my calculator. Because what I'm about to do is graph this by hand. So when you're doing stuff by hand, feel free to plug it in the calculator, get the decimals. So you guys with me? So whatever the shit that is, I don't know. Sounds about right. 1.2 something?
Yeah.
If you round it, is it one? You're gonna do it by hand. So
It's like close to
1.29.
1.3?
29.
So 1.3. By hand is hard to do even a first decimal place. Do you agree? But I know it's gonna be a little over 1. Okay. That's all that matters. So we got 3 intercepts. Let me put plus or minus here. Is everybody with me so far? I should go back up because I didn't finish this part. Is there a minimum? Is there a local min? Yeah, where is it? Yeah, so there's a minimum at -1. Now what am I going to plug -1 into? I got F double prime, I got F prime, and I got F. Which one? F, because I want to know where the function, I don't care how the function's moving, that's F prime, and I don't care if it's moving faster or slower, that's F double prime. I care about where it is, that's F. So if I plug a -1 in here, what do I get? Yeah, -5 plus 3, I get -2. And what's the maximum? Is that 1? Yeah, 1, 2. So let's plot that. So I got, let's see, where am I at? So I got 0, 0 is an intercept. I've got 1.30 and -1.30 are intercepts, yes? I've got, what did I just say? Oh yeah, -1, -2 is a minimum. And then 1, 2 is a maximum. I'm not just putting this label on here because my teacher wants me to. I'm doing that to help me when I graph the damn thing. If I go through this point, I've done something wrong because that's supposed to be a max, yeah? Local max, okay. Do we have any inflection points? Or any inflection point? Now, local min, local max is where the derivative changes sign. Inflection points is where the second derivative changes sign. How many times does the second derivative change sign? No. 1, 2, 3. So it changes sign here, here, here. So one inflection point is 0, 0. Is that cool? Where I know it goes through 0, 0. Another inflection point is, let's do this. Rad 2 divided by 2 is about 0.7. It's a good thing to know. And when I plug a 0.7 in to my function, I get something that somebody's going to help me with. What's 5 times 0.7 cubed minus 3 times 0.7 to the 5th power? Let's see, we're around 2, 15, 7.5. 1 minus -7. No, wait, negative. Yeah, what'd you get?
1.21.
1.21? Oh, I'm looking at the wrong damn thing, Jeff. Damn it. I'm trying to do it in my head and looking at this. I'll take 1.21. And when you plug in a -0.7, you should get -1.21, I believe. Is that true? So this is an inflection point. Alright, let me show you something kind of neat. Do you see how everything's happening right there? Okay. And this, I'm definitely going to take this to the next time. who gets to set the scale on this? Me. Beautiful. This is something you guys don't get to see very often. This is something I wish I would have realized earlier. Do you see how everything's happening really close to frickin' 0 and 1 and all that stuff? Don't you wish we had given ourselves more room to kind of live in? So, it's a good thing you guys do everything in pencil like you're supposed to. I could define this scale to even be like, well, how far up do I have to go? The farthest out I have to go is 1.3. Is that true? Yeah. So if I make this 0.5, I could even make this, let's see, 2.5, 5, 7, 5. Yeah, I could make this 0.25. Watch this. 0.25, 0.5, 0.751, 1.25. That's pretty good. Negative 0.25, negative 0.5, negative 0.75, negative 1, negative 1.25. That's pretty good. So now I've given myself more room to live in, yes? Okay. So 0, 0. Let me kind of collect my stuff here. Inflection points 0, 0, 0.7, 1.21, negative 0.7, negative 1.21. Then it goes through intercepts 0, 0, and plus or minus 1.30. And, where'd it go? Max is, where did my max go? There it is. 1, 2, min, negative 1, negative 2. Okay. So negative 1, negative 2, see how now I got a lot more room to live in, yes? And 1, 2. Maximum at, Jeff, you just wrote it, there it is. There's a min at negative 1, that's what you just put, good job. That's a min, max. My inflection points are 0, 0, 0.7, 1.21, and negative 0.7, negative 1.21. So these are inflection points. Okay, I like it. I feel like I'm missing some. Oh, what was my intercepts? Here we go. There's an intercept at negative 1.3 and an intercept at positive 1.3. There we go. Now, watch this. This is so cool. You ready? So all I have to do is get started. It starts concave up, right? That's the first thing it is, concave up. Okay, so see, watch. Concave up. There's an inflection point, yes? You guys see that? I labeled it for myself so I knew what the hell's going on. So right there's an inflection point. So now it becomes concave down, and then there's an inflection point, yes? So if you label each point, I know it's concave up. I labeled that IP, so now it's concave down. You guys see that? Now there's another IP. Now it's concave up. Now there's another IP. Now it's concave, down, and then it goes like that. So if you label each point what it is, as you graph, you know what to do when you hit it. That's a min, so I know I'm not going to go past that. That's an inflection point. Now it's going to be concave down. That's an inflection point. Now it's concave up. That's an inflection point. Now it's concave down all the way through. Now it's a max. I don't go beyond that. Maybe. Again, we did that really quick. That's the only one we've done so far all the way. So tomorrow we're going to finish up 4.2 and 4.4, and then the rest of the time is going to be practice review. I'll have the answer key for the practice test tomorrow. I'll do another problem like this that's a little more room in the first place. Yeah.
So I know that this worksheet is both 4.3 and 4.5. What steps are 4.3?
4.3 is the calculus. 4.5 brings in like asymptotes and multiplicities and such and behavior elements.